welcome you to another week. Today, we're going to start with what we call predict the response variable. I listed this particular lecture material for last week, but I'm bringing it to this new week because we covered a lot last week. The purpose of, study relationship among variables is just for us to have a way to predict one variable from the other. I remember when we started, we try to explain and predict the world. Okay, that's exactly what we do. And what are we predicting? Basically, we want to predict the response variable. The response variable is also called dependent variable. Okay, so in the outline, I'm actually going to say that we have ways to predict, like say that you are predicting individual or you're predicting me. If you look at the first one, I said predict Y. Y is the response. And when you predict individual, we also predict average. That is what we call the expected value of Y given X. Okay, so predicting individual, also predicting average. And we're also going to have interval estimation for our prediction. Because when you make a prediction, you're going to have a single result, right? You're going to have a single result. A single result could be wrong or right. If I really want to know how precise is my prediction, then we need a confidence interval as well. Okay, so let's get started. I'm going to start with this data set. There's there's a website called Rate My Professor website, where students rate their professors across some variables like quality, clarity, and so on. There's a lot of variables. And they rate their professor from a scale of 1 to 5, 1 being worst and 5 being the best. But you know what we want to do here? We only want to focus on 2 variables, quality and clarity. We basically want to see, if I know the clarity of a professor, can I actually predict the quality of that professor? And that is the reason what I'm displaying to you now is a scalar plot, okay, which shows the grammatical plotting of quality against clarity. Clarity is X, okay, the quality is Y. So which means what we want to predict is quality. And as you can see, most of the point landed on the straight line, which that's an indication of a very strong relationship. Now, take a look at this. This is a research question. If I know an instructor, of course, based on the assignment that I gave last week, when I asked you to identify which one is a prediction, which one is a explanation. Of course, when you hear if this, that's a prediction. Okay, so if I know an instructor clarity rating, okay, what can I say about the instructor overall quality rating? Now, instructors become its observational unit here. Students actually rated 366 instructors, okay, on these 2 variables. Now, of course, if you use the method that we used last week, we're basically going to have that. We have the estimate for beta naught, we have the estimate for beta 1. Why am I putting cap on the quality? Don't forget, that is the way we write fitted model. The fitted model is written as y cap equal beta naught cap plus beta 1 cap x. So there's always going to be a cap on the response variable. If you write it this way, If you don't put a cap on Y, that's wrong. Please take notes. Now, this is a module now, right? Don't forget, I said let X represent clarity, Y represent quality. Okay, now, if I want to use the plot to make a prediction, okay, maybe when the clarity is 3.5, I can use that particular scatter plot to determine what the corresponding quality is going to be, or I can make use of the equation. I can, or what I just need. So this is what I want to ask. Take a look at this. At the beginning today, I said, well, you want to make a prediction. Do you want to make an individual? Are you interested in individual or in the average? Now, take a look at this. This is an individual. You know why is it an individual? I said, if a specific professor, I'm referring to a particular professor, maybe me, right? If a specific professor clarity rating is 3.5, what is his or her quality rating? That is individual prediction. That is not average prediction. Okay, now all what I'm just going to do. Now look at the second one. What is the expected mean quality for professors? That should be the average one. Did you see the way the two questions are being framed? The first one centered on individual prediction. The second one centered on the average. And when you want to talk about average, then it means you're going to need more than one professor. That was why that professors is being pluralized. You got professors. Any question on that? Okay, now you're going to be surprised now. The result that we're going to have for the two will be the same. Clarity 3.5. And in the second one, also clarity 3.5. Okay, we're going to have the same result. But what kind of model am I going to use if I want to make individual prediction and if I want to make an average prediction? Now, take a look at that. For an average, for individual prediction, it will involve error. Look at that. You see the model involving error. Okay. Now, for collective one, there's not going to be error. You see the two equation. Now I'm replacing X with 3.5 because for the two, the clarity is 3.5. Now the difference in the module now for predicting individual response and for predicting average response is just the difference of the error. The error is in the individual one. The error is not in the average one. You know why the error is not in the average one? Because we have already assumed that the expected value of that error equal to 0. That is why you don't see error in the average one. Any question on that? But in the end, now take a look at what we have. The first one has error in it. The second one does not have error in it. Take a look at that. Now, that is that. Now, what if they want to ask a question? Why is dash? Why is it a known parameter? Is it an unknown parameter? Is it a random variable? The Y star is applicable to somebody, a person, right? Okay. And if I decide to go for another person, okay, two different individuals are not the same, right? Because of that, it's going to be a random variable. Does that make sense? And why is it random variable? Look at the equation. It is depending on the error. Do you see the first equation? Y star depending on error. There's error in the module for Y. Do you see that? That we account for individual differences. Okay, that's why it's a random variable. Okay, and of course the expected value of Y, which is a mean, that one does not include error if you look at the module. Okay, and therefore we can refer to that as a known parameter. We already know that. Okay, now what I'm trying to say now, whether I'm using an individual one or I'm using the group one, we are going to call the average one. If the predator is the same, I'm actually going to get the same results. Okay. If I've already now, you know, the other time, we've already obtained the beta naught beta 1, right? I show you from the beginning. We've obtained the beta naught beta 1, right? Right? We've obtained the beta naught to be 0.221, right? We've also obtained the beta 1 to be that, right? Whether I'm talking about individual one or I'm talking about the average one, I'm actually going to get the same result for the point estimate. It doesn't matter whether there's an error in it or there's no error in it, which I'm going to show you now. Do you see that? In the first one, okay, when I plug in 3.5, I got 3.55, right? In the second one, when I plug in 3.5, I also got 3.55. But the only difference between the two is going to be the interpretation. Let's look at the first one. How is it interpreted? We said the oh, go ahead. Y cap. That's like a predicted response. You know, there's a difference between Y cap and Y. Y is just the actual observation, the original values of the response. But the Y cap is the one you want to use your model to predict. Does that make sense? And that's exactly what we want to do now. If I have already gotten this guy and this guy, if I've gotten this guy and this guy, and they give me values of X, then if I want to predict Y, it's going to be a cap. Okay, so what I'm trying to show you now, okay, we're getting the same results, either for individual prediction or the average one, but the interpretation will not be the same. Look at the first interpretation. The estimated quality rating for a specific professor who has a clarity rating of 3.5 is 3.55. But look at the other one. The estimated mean of quality rating for professors who have clarity rating equal to 3.5 is 3.55. Do you see the difference in the interpretation? One focuses on individual, the other one focuses on the mean. So, but in the end, the point estimate, what do I mean by point estimate? What do I mean by point estimate? Point, you know, in statistics, we have two types of estimates. We have the point and we have the interval. But let me tell you this, we cannot rely on point estimate because it's a single result. Okay? The point estimate is when you have a single result. Like what was the final result? 3.55. That 3.55 could be wrong or right, even if you have done, you know, what you are supposed to do. But how do we, I mean, to be at the safer side in research, if I really want to know, okay, I'm going to tell you why this is not reliable. How many times do we go into a population? Once. Maybe we took a sample, like here now, 366. If you go to that website, there are more than 366 professors. There are a lot. Now, do you know that if you also go into the population to choose 366, the value you're going to get for beta naught will be different from mine. If 1,000 investigators should go into the population, then we have a different value for this. Then we have a different values for this. You know what we did last week? We said that provided they follow what? Normal distribution. You remember? That provided this guy follow normal distribution, is going to have the mean of this, and the variance is going to be this. If you remember what we did last week, and this one also follow normal distribution, then we have the mean of this and the variance this. Okay, we are actually believing, even though we've gone into population once, we rely on central limit theorem that said that If n is at least 30, we should be fine. Okay, but I want to tell you, we cannot be totally fine. The fact still remains, we go into the population once. But the only way to tell whether we're actually going to be fine, completely fine in a way, we need to get interval estimation. You know, the interval estimation with, this is what interval estimation is going to tell you. The idea behind in an interval estimation, we use confidence intervals. Have you heard about confidence interval? Okay, confidence interval tells you how much, okay, how much the results, of your survey reflects the view of the overall population. If I really want to know how much the result of your survey, don't forget, when you are conducting survey, you're taking sample and you go into that population once. If I really want to know, how can we rely on the estimate that you got? How can we rely on 3.55? Then we need an interval. We need to construct a confidence interval. And in the confidence interval, we're actually going to consider margin of error, where we're going to consider error to the right and the error to the left. Does that make sense? And that's exactly what we basically want to do now. But before I go there, I told you the other time, y is a random variable, individual one. Then that one is, it's a parameter, and most of the time probably unknown. And those are the formula. But there's something I wanted to see. In the case of the estimator, you see that initially, when you look at the formula for individual, it involves error, right? The formula of the mean, expected value of y given x, does not involve error. When I now want to use data, when I want to use my sample, okay, I'm still going to use the same formula at the end of the day. That was why we were getting 3.55. We're getting the same results. Okay, now, and that was why I said the point estimate for these two quantities are equal. But if the point estimates are equal, what about their intervals? But let me tell you this, their intervals will not be equal. And let me tell you, the one that have a narrow margin of interval is the one that we're going to prefer. And which one? It is the one that has to do with the average. And that is the reason why statisticians like average a lot. You remember in this class, when I was explaining to explain or to predict, when I was using a tension called individual and the average, when I said statisticians normally focus on average effect. Average, not only statistician, psychologists, scientific community in general, will focus more on the average. And why do they have to choose average instead of individual? Because the interval of the interval of the average is narrower. Why the interval for the individual prediction, okay, is wider. And when the interval is narrower, then you can rely more on that particular estimate. When the interval is wider, then you can rely more on the estimate. Does that make sense? Okay. Now, how do I get the confidence interval? Of course, it's going to be point estimate plus or minus margin of error. The margin of error is when I multiply the distribution quantifier by the standard error. Okay. Now, I quickly want to remind you what you've done before in statistics, where you want to figure out the confidence, 95% confidence interval for mu. Okay, you normally make use of that formula. You remember you've done something like that before in your lower course in statistics. We now want to apply this knowledge now to predicting response. Now, I'm going to show you, I'm going to go there now. Okay, I want to start with the average prediction. Now, let me tell you this. When I'm talking about interval for average, we're going to be using the word confidence interval. But when we're talking about interval for individual, we're going to be using the word prediction interval. Please take note. Anytime you see us saying confidence interval, it means I'm seeking the interval for average prediction. When you hear prediction interval, then I'm seeking interval for individual prediction. Does that make sense? Okay. Now, I'm just trying to show this is the setup, but I'm basically going to show you because the same way, this follow normal distribution, and this follow normal distribution is the same way the prediction also follow normal distribution. Look at what I'm the prediction now. Y cap, the difference between that and that, but you don't necessarily need that. This is what you need. Now, if you want to get a confidence interval, you need a standard error, right? And the quantifier. How will I get my standard error? Now, if I'm working on mean, okay, I'm actually going to get two it depends on the situation. In a normal distribution, there are two parameters in a normal distribution, mu and standard deviation. Now, and now this mu is the same thing as the expected value of y given s that I'm talking about. Then I will now consider two situations. One is sigma known. Two, if it is unknown. So if sigma is unknown, I'm going to use this guy as the standard error formula. If sigma is known, I'm going to use the other guy. Any question? Take a look at that. What is the difference between the two? The difference between the two is just like this one has a cap, because when the sigma is unknown, then you're going to estimate it from the data. But if it is known, that means you are giving. You don't need to estimate it. It doesn't have a cap. Any question? Any question? And let me also tell you this. If it is unknown and you are the one that estimates the standard deviation, you're going to use T in your quantifier, T distribution. But if it is known in your quantifier, you're going to use normal, like a Z. Does that make sense? Okay. Now, go ahead. Yeah, a situation where they're going to tell you, like, we normally have an assumption in statistics. They're going to say, okay, if the standard deviation is unknown, okay, they will tell you, okay, if whether it is going to be known or unknown, of course, the examiner is going to tell you. But if it is unknown, of course, we have data sets that we can use to estimate that, except that the distribution multiplier that we're actually going to use is what is going to make a difference. One is using T distribution, the other one is using normal distribution. Okay. In that case, now that is the one on average prediction. Now, if I'm talking about prediction interval, which means I'm talking about I'm seeking confidence interval for individual. I told you the confidence interval for individual is what we call prediction interval. But the confidence interval for average prediction is called confidence interval. Okay, now let me tell you what is going to be the difference. You're going to see now. Take a look at this. The standard error will be different. I want you to pay attention to something. Can you see this standard error? There's a 1 plus inside, right? Look at the last expression. There's a 1 plus inside, right? Now, take a look at the last one, the previous one. Do you see 1 plus inside the square root? No, that is different. The one with the mean does not have 1 plus. But the individual one actually has plus 1 more. Look at that. 1 plus. You see that? Now, and I want to take you to, this is it now. Let's say I want you to find, look at CI. What does CI represent? Confidence interval. It means I'm interested in the mean. The same thing, another way, another name for mean is the expected. But when you see PI, what am I interested in? The confidence interval for individual. Now, look at the two formula. Now, somebody should spot a difference. What is the difference in these two formula? The standard error. You know, the first, if you look at the standard error for the confidence interval, there's no 1. But in that one, what do you see? 1 plus. Do you see? Now, mathematically speaking, the standard error of the prediction interval is higher than that of the, you know, the confidence interval. And that was the reason why we don't prefer prediction interval. We don't prefer the individual one. We prefer the average one. Okay? They have every other thing equal, except what you see in the square root. The whole thing that you see, apart from the 0.975 quantile from whatever is what we call, and you know our assumption here, we're actually going to estimate our sigma. That was why you see a Y cap. And we're going to be using a T distribution. Does that make sense? Okay. Now, I want to go back to the question we're solving. Don't forget, for a particular professor, Professor John, whose clarity rating is 3.5, okay, we have already gotten the quality to be 3.55, but we want to obtain the confidence in 95% confidence interval. What kind of confidence interval do we want to do now? That would be prediction interval, because we're focusing on individual, Professor John. Then we're going to use this formula here. Look at that. The one that have in the square root 1 plus. Okay. So look at the question that I asked here. I said, is this a confidence interval or a prediction interval? Of course, the answer is a prediction interval, because we're only focusing on Professor John, an individual. Go ahead. Oh, you said in most cases we don't want to do point estimate, right? Yeah. No. This one now. Oh, that's a very good question. When I say point estimate, in statistics, when you get a single result, that's what we mean by points. It doesn't matter whether I'm doing average or I'm doing individual. The fact that the result that I got is, you know, what do I mean by a single result? You know, the other time we got 3.55, right? 3.55. This is a single result, like single result. Now, getting single result is dangerous. Yeah. Now, I'm now justifying now, you know, the essence of this class now is trying to justify that the reason why we don't need a point estimate. Do you know that when you go to some research article today, I'm seeing some research article where they only publish point estimates, but you can now say, no way, the point estimate is not a good one. That's a very good question. Now, but another thing is this: we know we need interval, right? But we still now want to prove to the world that we don't need interval for individual, but we need interval for the average. And they're going to ask you, why is it that we don't need interval for individual? You're going to say, oh, because the error associated with that of individual is going to be more than that of the average. But in statistical analysis, we focus more on reducing error. Okay, now take a look at that. Now, Of course, you know, if I want to start, whether with the prediction interval or with the confidence interval, I will four of us get my point estimate, right? Which is what we got it to be 3.55. Now, I want you to pay attention now. Don't forget, do you see 0.975 quantile? How do we get that from R? What is the meaning of 0.975? Take a look at this. This is what I mean. If I'm dealing with 95% confidence interval, what is the meaning of this guy? 95% confidence interval means if I have 100 interval, even though I've gone into population once, now I'm now assuming if I go into population 100 in 100 times and I compute 100 intervals, okay, the true value will lies in 95 out of the 100, which means we're actually going to mislead the world. How many times out of 100? 5 times. Okay, now that is going to be 1 minus alpha over 2. This guy here is the confidence interval, which is 0.95. The alpha is 1 minus confidence interval, which is 1 minus 0.95, which is 0.05. So you're going to do 1 minus 0.05 divided by 2. So this guy is going to give you 0.975. Does that make sense? Now, if you now want to get the quantifier using T distribution, you're going to write QT, P equal to 0.975. You know, right now, you give you 95%. In another question, it may be 90. It may be 99. Does that make sense? Okay. Now, comma, DF, the degree of freedom is N minus 2. Where am I getting my 2 from? Because there are 2 parameters, beta not beta 1. By the time we start multiple linear regression now, we're not going to use N minus 2 anymore. Maybe we're going to be using N minus P, where P now represents the numbers of parameters. Does that make sense? Now, when I plug that in, that will give me 1.97. Now I got my quantifier now. What is the next thing that I need to compute? I need a standard, standard error. Okay. Now, this is what you're going to do. If I go into R, if I have my data in R, and I regress quality on clarity, the name of the data is rate professor. I'm actually going to have this output. Now, if I want to get this guy manually, I already know my hand in the, in the formula. I know my hand, right? That is the number of professor 366. What is the sigma cap? Let me show you. Please pay attention. The sigma cap is, see that? That's a sigma cap. The residual standard error. Okay, you see that? From the arrow output, residual standard error is the sigma cap. Then the mean, if you need X bar, if you look at the formula, that would be the mean of the class, okay, which is basically going to be here. Do you see that? Look at that hop. Mean into rate prob $ clarity. That will give you that, right? Okay. Now you see that, and your N is 366. Okay, your X bar now is 3.5. Okay, and of course, if you plug all that in, but let me tell you this, you don't need to waste your time. We have a code in R that will save you all the time. And let me show you the code now. Oh my God, easy code. Take a look at that. If you want to get a code, look at that. Predict MOD. Where's my MOD? You have to come back here. You see up, MOD equal LM, quality on that. Okay. Now, MOD, comma, new data equal to data.frame. Then you now indicate the value of your X. When you do that, oh my God, if I want to get the confidence interval, the one for the mean prediction and the one for the individual one is going to be the same code, except look at the interval. What did I write on the interval? Confidence. The other one, what did I write? Predicts. You done? Any question? Oh, R is easy. And you know what? We're basically going to be using R. When I ask you to find the confidence interval, the prediction interval, you don't need to waste your time like using the formula. But why am I showing you the formula? Is just for you to know what happened behind the scene. Now, let us now judge. Which one has a wider range? You know, the lower endpoint in the confidence interval is 3.5, 32898 to 3.57. And the one in the prediction is from 3.19 to 3.91. Which one has a wider range? The prediction interval. And that is the reason why statisticians prefer average. Any question? Look at that. Even though they have the same value for point S, but the interval is not the same. Look at that. We can decide to, okay, so this is all what we have. I just bring that out now. The result, you know, C high, the interval for average. You know, where did I copy that guy from? From the result here. The lower endpoint and the upper endpoint. I'm trying to tell the world what I got, what I got for the CI for average and for the prediction interval. Why did I indicate that one, the other one in red? The one I indicated in red is that don't go there. That is going to give you a wider range. How many more minutes do I have? Like 10 minutes? Like, oh, 15. Oh, okay. Now, any question? So do you know what we've done today? Mathematically speaking, we've been able to show that or verify that the prediction interval is going to be wider than confidence interval. And that is the reason why statisticians will focus more on the average. Okay. Now, I want to go into, I'm going to use another data set now. I think I used this data set last week where we're actually regressing BP on, you know, that response variable. And what is going to be the mean function here? The mean function is just for you to bring out what is the combination, what is your beta naught, minus 42.1378 and the BP. Okay, so that is what I put there, right? And of course, from the output, you know, I can ask you so many questions like, looking at the, you have a data set and you run this. What is your mean? What is your X bar? What is your Y bar? What is your SSS? What is your XY? I think I showed you all this last week. Okay, so make sure you. Okay, another thing I want to show you now. What we have done, what we just did now, using a computer, using a R software. I also want to show you how you can do that using manually. Look at that. Which one do you think I'm doing now? That is the standard error for what? For individual. You can say 1 plus 1 over n. So what if in a situation, because at times I can give you some values and I ask you to compute the standard error associated with individual prediction. I can even ask you to do that manually, but I'm going to give you a lot of information. Now, if you know, equation 2.17, that represents the standard error for individual, for individual prediction, right? All what you just need is what is the value of sigma. Yeah, they say, oh, sigma is 0.379. Oh, where is the 0.379 coming from? Oh, it's coming from. You know, you ask a question, right? You ask the question, the other time that how is that sigma determined? Like, so of course, let me tell you, the sigma is not going to be given when you're working with data in a real life practical situation. You're going to be the one that will figure that out from your data. And that is always going to be residual standard error. And if I ask you to determine this, sigma cap squared. You just square that. Any question? Okay, just wanted to take, okay, go ahead. Oh my God, that's a very good question. You know, we have so many errors. Why? I'm going to show you now. You know, initially, this is what I have, right? X and Y. Okay. And I finally got this guy using what? Using the module. How am I going to get this guy? The moment I get this and this, then for each value of S, if I plug it, I'm actually going to get different Y cap, right? Then from there, I'm now set to get my error now, which is Y minus Y cap, which is going to be the original response. Then this is predicted response. So which means the number of observation, that was going to be the numbers of the errors. It means I'm going to get a lot of errors, right? Now, residual standard error is going to tell you the deviations around the error, because you have so many errors, right? You have so many errors. So that is why the residual standard error is just basically going to tell you, if you want to measure how far apart on average the errors are from each other. Does that make sense now? That's what we call residual. This is called residual. Oh, sorry, I'm going to pick up. So this is residual. Okay? No. Technically, they are the same. Error is when I'm focusing on the hope. You know, I'm using, you know, here, the data set that we're using, we're focusing on the sample, right? Right? But if I'm focusing on the whole population and I'm doing this, then it's going to be, I'm going to be calling that error. So the two are the same, but in statistics, the one, when we are focusing on a sample of data, you're basically going to be saying residual. And let me tell you this. On a normal ground, we can't get this guy. Why? That is unexplained. That is unexplained. But what do we now do? If we now want to have a way to manage that, you know, we want to manage this guy, right? We want to bring it under control. We want to minimize it. You now know what we're going to do? We're going to estimate it. Having a cap is estimating the unexplained. Does that make sense now? You know, you guys make me happy today because you ask questions. You know, the more question you ask, the more, you know, you're going to get more of the information around here. Now, can you now see? So in a way, we are estimating error. Exactly. So laterally, it should be called error, but we can't call it error. We're going to say an estimated error. So estimated error is residual. Okay, now, good job. Okay, now in the end, you know, the moment I got my standard error, all what I just need to do is multiply by quantifier. This is this guy here. I just, this 2.95 is the quantifier. You know, what I got from you know, T distribution. And at the end of the day, look at that. That is the range, right? Okay. You know, this is for the prediction. Okay, the same way. This is just okay. Let me just tell you. Oh, I got 5 more minutes, right? Okay, I'll quickly explain this. What is the meaning of 2.18? You know why? I want to talk about coefficient of determination. What do we mean by that? The coefficient of determination will tell us out of 100% variation in the response, how much does the module explain? You know, module cannot explain 100%, right? Now we just talk about clarity and quality. We believe there is 100% variation in quality. How much of that Okay, does the clarity explain? If I really want to know, then I'm actually, the R square is going to be this guy. R square is going to be explain variation divided by the total variation. Explain divided by the total variation. Now look at 2.18. The SS reg is explain variation. SS reg, sum of square regression. That is explain variation. SSYY is the total variation. Why is it YY? That is the variation around the response. What is ROSS? Residual sum of square, which is the unexplained. Now let us see whether it makes sense. Total variation minus unexplained will give you explain. Does that make sense? Total variation, the SS reg, so which means the XYY is XX reg plus ROSS, which means total variation equal explain plus the unexplained. I think that makes sense, right? Okay. All those ones are just, but this is what we need. Well, what do you see here? SS reg is the explained variation. SYY is what? Total variation. The ratio of that, do you know the meaning of that 0.995? Oh my God. Out of 100% variation in the response, the module explained 99.5%. The R square will actually tell us how good is the module. That's the goodness of it. But let me tell you, it is not all the time. You can trust that when the independent variable, when the explanatory variable is more than one, like when we have like so many independent variable, maybe from 3 and above, we can't trust R squared. We're still going to do that in this class. Instead of R squared, we're going to be talking about adjusted R squared. Has anybody heard about adjusted R squared before? Okay, we're going to do that in this course. But up to 3 variable situation, we can still trust R squared. Okay, so a time is coming in this class where I'm going to tell you when you decide to increase number of predictor in your model, even though if that predictor doesn't make sense, the R square is going to go up. But in that case, you can't trust R squared, then it needs to be adjusted. But right now, we don't need to adjust that because we only have one predictor variable. So what R squared measure is just, and how can you see R squared in the body of your output? Like if you do R, this is your R squared. R will oh my God, pay more attention to R. R will give you a lot of results. Look at that. In this result, there's estimate, there's standard error, there's p-value. I'm still going to explain all of that. There is a residual standard error, there's multiple R square, there is even adjusted R square that I just talked about. Everything here is what we're going to do here. Any question? This is going to be the end of my class today. Any question? Now, what I normally do during the 3rd week of my lecture, I need you to send me a message today. I need you to tell me what you get stuck with in this class. I need you to tell me whether you really understand everything that we've been doing from day one in this class, because I want to hear from you. I want to see whether I should, take it, I should slow down a little bit, or I should keep going in the way I'm going, or there's something I just need to clarify. I want to hear from you. Does that make sense? Please send me a message today. Okay, make sure you stay safe and have a beautiful day. Bye for now, everyone.